I want to talk about another specific example of a type of differential equation. This is one that's related to something that we've seen before. So this is called, it's got a terrible name, homogeneous linear differential equations with constant coefficients. And these are equations that look like this. So you can see here I've got, this looks very complicated, but basically what it is we've got a constant times the nth derivative plus a constant times the n minus first derivative, all the way down to a constant times the first derivative plus a constant times x. So like a simpler version of this would be something like 3x triple prime of t plus 4x double prime of t minus 2x prime of t plus 7x equals 0, something like this. So you've got a constant times a derivative, constant times another derivative, constant times another derivative, constant times x, and finally equals 0. Okay? So anything like this can be solved in the same way. Okay? So any equation, differential equation that looks like this is going to have solution x of t equals c1 e to the lambda 1t plus c2 e to the lambda 2t all the way up to c n e to the lambda n t. And so this should look familiar. So this should recall something we did at the beginning of the semester where we had homogeneous linear difference equations, right? And we found these constant exponential terms and said, oh, it's going to give you this exponential behavior. And it was based on the roots of a polynomial. So all these lambda i's were roots of polynomials, and this is exactly the same situation where the lambda I are the roots of the polynomial a0 x to the n plus a1 x to the n minus 1 all the way down to a sub n minus 1 x plus a sub n equals 0. Okay? And so that determines the lambda i's. The constants are going to be determined by initial values. Okay? And so if you've got a certain number of initial values, you can figure out what all the different constants are. Okay? Now, notice that we've got n constants, c1 through cn. That means that we're going to need n initial values. Okay? So we're going to need an initial value not only for x of t, but also for x prime of t, x double prime of t, and x triple prime of t. Okay? And so let me give you an example of this, and then we'll talk about the general behavior. So let me see if I can think of something that's actually fairly easy to do. I've got an example here. So let's look at the differential equation x double prime of t, so the second derivative of x minus, and I'm just going to write x double prime. I'm not going to put everything. Minus x prime minus 6x equals 0. Okay? So the corresponding polynomial that we want to find the roots of is x squared minus x minus 6. All right, that's actually, rather than x's, let's say lambda squared minus lambda minus 6 equals 0, right? Because we're looking for those lambda values that were in our exponential equation. We can factor this, lambda minus 3, lambda plus 2 equals 0. And so what we get, lambda equals 3 or lambda equals negative 2. And so our solution is x equals some constant times e to the 3t coming from this plus some constant times e to the negative 2t. Okay? And so that's going to be our equation. And if you think about kind of finding the constants, we would need to know not only what x is at 0, but also what x prime is at 0. So you would need something like, say, x of 0 equals, say, 2, x of 1 equals, or x prime of 0, right? So you need something for both the function and for the derivative. So x prime of 0, say, equals 1. X of 0 equals 2 is going to give you a value for this. X prime of 0 equals 1 is going to give you the value for the derivative, which is easy to take. 3c1 e to the 3t plus, minus rather, 2c2 e to the negative 2t. And so if you plug in t equals 0, x equals 2, from this one you're going to get 2 equals c1 plus c2. From this one, x prime of 0 equals 1. Plugging in t equals 0, you're going to get 1 equals 3c1 minus 2c2. And so from that, then you can solve and figure out what c1 and c2 are. I don't actually know. Let's see. 5c1 equals c1 equals 1, c2 equals 1. Oh, that works out very nicely. Okay? And so for this differential equation and these initial conditions, the particular solution is going to be x equals e to the 3t plus e to the negative 2t, because c1 is equal to 1 and c2 is equal to 1. Okay? And so you can get an actual particular solution. Okay? So that's just kind of an example of how this works. Let's talk a little bit about behavior. So what does the equation, if we go to this solution, right, we've got this particular solution, or even just the general solution, x equals c1 e to the 3t plus c2 e to the negative 2t. How is this solution going to behave? Okay? Well, so you've got a term that's growing exponentially and a term that's decaying exponentially, and you're adding them together. So what is that going to look like? Okay? Well, the bottom line is that the largest value is going to overwhelm everything else. Okay? So you've got this e to the 3t term, this e to the negative 2t term. This term is going to dominate, and we're going to get exponential growth. Okay? And so in the next video, for now, so let's go ahead and talk about kind of this idea. So here, this 3 is the largest of our lambdas. That's going to be our dominant value. Just like when we had dominant eigenvalues, it's going to give us the same way. So that's going to dominate the behavior of everything else. So whichever lambda is largest, let me actually say the absolute value of lambda is largest, will dominate the behavior. Right? So 3 being larger than negative 2 means that that's going to dominate the behavior eventually. And we can split this up in much the same way that we've thought about this before. So for the dominant lambda, which means that the largest absolute value. If lambda is greater than 0, we'll get exponential growth. If lambda is less than 0, we'll get exponential decay. Again, eventually, right? It might not start out that way, but eventually this is going to be kind of the end behavior. If lambda is equal to 0, we'll get stability, an equilibrium, right? It'll eventually kind of come to a constant. In the situation where lambda is complex, right? So all of these lambda were real values. If lambda is a complex number, right? Because we're taking roots of a polynomial, so it could be a real number. It could also be a complex number. Then we're going to have 3 different situations, okay? So this comes down to the real part of lambda. So if lambda is equal to a plus bi, if a is greater than 0, we get what's called undamped oscillation. So undamped oscillation means that it's going to be going up and down, but the amplitude is going to get larger and larger. So undamped oscillation would be something like this, where you've got this kind of curve, but it gets bigger and bigger and bigger as it goes out. Okay? If a is less than 0, we'll get damped oscillation. Which is the opposite, right? So that's where you've got values, but it's getting less and less and less in the oscillation as you go along. So it's dropping down. And if a is equal to 0, we'll get stable oscillation. Okay? So if you've got a real part that's equal to 0, you get stable oscillation and it'll be fixed. Okay, and the reason for this kind of oscillation, which might seem strange, for those of you who've seen a little bit of complex numbers, you'll remember that if you've got, say, lambda is a plus bi is a complex number, e to the lambda t is going to be e to the at plus bit, right? And if you remember kind of splitting this off, this becomes e to the at, e to the bit. If you remember from complex numbers, there's a formula called Euler's formula, which lets you rewrite something like e to the bit as cosine of bt plus I sine of bt. And so your oscillation is coming from this trigonometric term. So that's where that's coming in. The reason why it either grows exponentially, you get that undamped oscillation because you're multiplying by something that's growing exponentially. If a is greater than 0, you get damped oscillation because you're multiplying by e to the at where a is less than 0, so it's decaying. Or if it's e to the 0t, then it's just stable and it's a constant. Okay? And so those are the different kinds of behavior that you can see. Okay? So I think that's everything that I want to say about this. So we'll end this lecture here.